All right, welcome back to another edition of The Explainer. Today, we're diving into something that literally happens in your pocket 100 times a day, computer vision. We're going to look at how machines use raw math to actually see and process images. I mean, when you snap a photo, how does your phone actually know what's a face and what's just the background? Well, it all comes down to math. So let's just get right into it.
Here's a quick look at the roadmap for today's explainer. First, how computers see edges. Then, types of edges. Number 3, finding edges with Sobel. 4, the Laplacian approach. 5, smoothing out the noise. And finally, real-world camera filters.
Section 1. How computers see edges.
Think about this for a second. When you look at a coffee cup sitting on a table, your brain instantly separates that cup from the table, right? But a computer, it just sees a massive grid of numbers, just values representing pixel brightness and color. So how on earth does a machine know where the coffee cup ends and the background begins? What's the mathematical trigger that screams, hey, there's an object right here?
The answer lies in a really simple concept, an edge. To a computer, an edge is basically just a boundary, or a contour, where the image intensity, meaning the brightness or the color, changes super sharply over a short distance. These rapid intensity jumps are absolutely crucial. They give computers structural info. They tell a machine where an object boundary is, or if there's a change in surface orientation, or even just lighting shifts. Without finding these edges, the computer is honestly completely blind to the structure of the real world.
Section 2. Types of image edges. Now that we've got the basic idea, let's look at the different profiles these intensity changes can actually take. Think of this like a cliffs and valleys analogy. If we mapped out pixel brightness like a topographic 3D map, a step edge is essentially a sheer cliff, just an abrupt, sudden drop from light to dark. A ramp edge is, well, more like a gentle rolling hill where the intensity changes gradually. And a roof edge, that's like a mountain peak or a ridge, which usually pops up when you have lines in an image that are thinner than the filter itself. Getting a handle on this topography is exactly how we start writing the math to find it.
But here's the kicker, and this really highlights the difference between theory and reality. In a perfect math textbook, we'd only ever see the ideal step edge, a totally instantaneous jump from a dark pixel right to a bright pixel. But, your camera lens isn't perfect, the lighting in your room isn't perfect, so in reality, what we're almost always dealing with is the realistic ramp edge. That transition from an object to the background actually takes a few pixels to complete, creating a slope. Our math literally has to be smart enough to handle that ramp.
Section 3. Finding edges with Sobel.
So how do we actually find those ramps and cliffs mathematically? Well, let's look at a true classic in computer vision, the Sobel operator. Now don't let these matrices freak you out. Let me explain this with a super clear example. These are just little 3x3 grids of numbers, known as convolution kernels. We've got gx for the horizontal gradient and gy for the vertical. Let's just look at the gx matrix on top. See that 2 right in the center row? And the -2 across from it? That is not random. By putting a heavier weight of 2 on the pixels right in the middle of the edge we're looking for, the Sobel operator actually creates a built-in smoothing effect. It kind of averages out random camera noise while still locking onto that sharp vertical cliff. It is just a beautifully elegant piece of math.
So how does the computer actually apply this? It's basically a two-step scanning sweep. Step 1, the computer takes that JAX kernel we just looked at and literally slides it over every single pixel in your image, left to right, top to bottom. This calculates the horizontal derivative, which effectively highlights all the vertical edges. Think like the straight vertical sides of a skyscraper. Step 2, it does the exact same thing but with the GY kernel. It slides it across to calculate the vertical derivative, locking onto all the horizontal edges, like the horizon line.
Okay, so once we have both the horizontal and vertical data, we've got to combine them to get the full picture. And this is where some basic geometry comes to the rescue. To figure out the overall strength, or the magnitude of the edge, we literally just use the Pythagorean theorem. We take the square root of gx squared plus gy squared. Simple as that. And to find the exact direction the edge is pointing, we use a little trig, the inverse tangent of gy divided by gx. Boom. From a basic grid of pixels, the machine now knows exactly where the edge is, how intense it is, and which way it's facing.
Section 4. The Laplacian approach.
Sobel is a fantastic tool, for sure, but it's definitely not the only way. Let's step up our game from first-order to second-order derivatives. Let's really compare these two. Gradient-based operators, like our friend Sobel, find edges by looking for the absolute peak of the first derivative. Imagine you're climbing a hill. Sobel is looking for the steepest possible point. But Laplacian-based operators? They go a whole level deeper.
They look at the rate of change of the slope itself, the second derivative. So instead of hunting for a peak, the Laplacian looks for a sign flip. It searches for that exact split second where the curve stops accelerating upwards and starts decelerating downwards. We call that moment a zero crossing, and it pinpoints an edge with unbelievable accuracy.
To actually find these zero crossings, we use these Laplacian kernels. Let's decode what this common 3x3 matrix is doing. If you apply it to a pixel and get a positive number, it means you're at a local intensity peak, the top of the hill. Get a negative number, you're down in a local valley. Get a zero, you're just standing on a flat, featureless region. The real magic happens when adjacent pixels suddenly flip from positive to negative. That zero crossing right in the middle, that is your computer jumping up and screaming, right here, I found the exact center of the edge.
Let's explain this with a really concrete example. Check out this matrix showing pixel brightness values in an image. Over on the left, we've got a really dark region, all values of 10. Then suddenly on the right, it jumps to a bright region with values of 200. Classic step edge, right? If we slide our Laplacian kernel across this, the flat 10s give us 0. The flat 200s give us 0. But right at that boundary, the pixel value leaps. The second derivative goes crazy. It spikes way up into the positives on one side of the jump and then plummets into the negatives on the very next pixel. That boundary line between the 10s and the 200s is our mathematical zero crossing.
Section 5. Smoothing out the noise.
Now, in a totally perfect world, the Laplacian would be completely flawless. But we need to pivot to the biggest headache in edge detection, unwanted noise. See, the thing about the second derivative is that it is hypersensitive. I mean, it reacts so aggressively to any tiny change that just the invisible, random static from your phone's camera sensor will cause fake edges to pop up literally everywhere. It turns the image into a complete mess of false zero crossings. So what's the fix? We actually have to blur the image a little bit first. We smooth it out using a math function called a Gaussian, and then we hit it with the Laplacian. It's a 1-2 punch that's actually so famous it has its own acronym, LOG, or the Laplacian of Gaussian.
But how do we actually blur something using math? Let me explain with another example, using the absolute simplest method out there, the averaging or mean filter. Look at this 3x3 grid. Every number is a 1, and the whole thing is multiplied by a fraction, 1/9. If you drop this kernel onto the specific pixel, what it does is add up the brightness of that center pixel plus all 8 of its immediate neighbors, and then it just divides by 9. It literally swaps out the center pixel for the average of its neighborhood. So if you've got one random super bright noisy pixel ruining your shot, this averaging process forcefully blends it right back down into its surroundings. It just smooths the whole spatial domain out.
Section 6. Real-world camera filters.
All right, let's bring all this together for the grand finale and look at how this math creates everyday magic in the devices you're probably holding right now. The problem with that basic mean averaging filter we just looked at is that, honestly, it's a bit too dumb. It blurs everything, including the very edges we just spent all this time trying to find. It has terrible edge preservation. It ruins the sharpness of the photo. Enter the absolute hero of modern image processing, the bilateral filter. This is a crazy advanced smoothing technique that calculates blurring based on not just how close pixels are to each other, but also how different their color intensities are. It fundamentally achieves the holy grail here. It completely scrubs away the random noise while aggressively protecting and preserving the sharp edges.
And this connects directly to your daily life. Whenever you open up TikTok, Instagram, or just use the default portrait mode on your phone, and you notice your skin looks, miraculously flawless, but your eyelashes and hair are still perfectly sharp and detailed, yep, that is the bilateral filter doing its thing. It's using this edge-preserving math to identify the sharp structures, your eyes, your lips, the edge of your jaw, and it protects them. Meanwhile, it applies a smoothing matrix strictly to the flat, ramped surfaces of your skin. This raw matrix math is literally the engine behind global digital beautification.
And I think that brilliantly illustrates the journey we've taken today in this explainer. We started by defining a simple math cliff, moved to using Sobel and Laplacian matrices to actually trace it, and finally saw how bilateral filters selectively blur the world around it. The math is just so elegant, and it's running seamlessly in the palm of your hand right now. But I want to leave you with a final thought. We are rapidly moving into an era of AI where neural networks are learning how to build these filters entirely on their own. So as these computer vision systems get more and more advanced, how will these fundamental mathematical matrices evolve next? Are human-designed formulas like the Sobel operator going to become completely obsolete, or will they forever be the underlying bedrock of how machines perceive our world? Definitely something to think about the next time you snap a quick selfie. Thanks for focusing in with me today, and I'll catch you on the next explainer.